All right, we're going to go through some final exam problems, and they're all based on your final exam review. This is what I did. I went through my problems on the test, and I picked out what the topic was that problem was about. There's going to be about 70 multiple choice questions, and every one of those things is listed here. If you know how to do all these things, you will get them all correct. All right, so you have to know the difference between accuracy and precision. Remember, accuracy, that is, if you're doing an unknown, that is how close you are to the correct answer. If you have the right answer, then you're very accurate. Precision is how close your results are for all three runs. If they're all three the same, then you have good precision. If all three are the same and they are all correct, then you also have good accuracy. If you have good precision, but all three of those numbers are wrong, well, then you have good precision, but you have poor accuracy. And if you have poor precision, but the average comes out to be the correct answer, well, then you have good accuracy, but poor precision. So know the difference between accuracy and precision. Physical change versus a chemical change. You have to know if it's just changing state, ice to water, water to steam. That is just a physical change. If you have a chemical property, you throw some sodium in water, then you have a chemical reaction. Sodium reacts with water. Any chemical reaction is a chemical change. But any density, boiling point, melting point, those are all physical properties. Conservation of mass. So that was the lab that we did. Conservation of mass, because it's very strange that when you burn something, all right, and so this is what we did in lab. We took magnesium and we burned it, all right, and so we weighed our magnesium, whatever, 0.5 grams, and then when we were done, we had to weigh the magnesium oxide, and of course I asked, after you burn something, is the mass going to go up or down? Common sense says the mass goes down. However, when you're burning a metal, and you're getting a metal oxide, that means you're adding oxygen to it. And so this has to weigh more. I don't know, let's go with 0.65 grams, whatever. All right, so whatever your data was. And then to get the mass of the gas, so in lab, very easy to weigh magnesium. It's a solid, very easy to weigh. Magnesium oxide, it's a solid. Very difficult to weigh the oxygen, that is a gas, but we don't need to weigh it. We just use our conservation of mass, which says it's your mass of reactants equals the mass of products. And to the fourth decimal place, that is a correct statement. Go out further decimal places or do nuclear reactions instead of chemical reactions, then you do not have a conservation of mass. But for chemical reactions out to the fourth decimal, yes, we have a conservation of mass. So just by subtracting, you get 0.1500 grams. All right. So make sure you know conservation of mass, how to do those types of problems. Sig figs, all right, well, we just did sig figs when we did our conservation of mass. So when you're adding and subtracting, it's a number of decimal places. When you're doing multiplication and division, then you're looking at the significant figures. All right, so when you add, subtract, the amount that has the least number of decimals, that's how many decimals you give in the product. When you're multiplying, dividing, the number with the least number of sig figs, that's what you give for your answer when you're doing multiplication and division. All right, and then over here to chapter 2, properties of metals, nonmetals, and metalloids. All right, so you need to know your periodic table. You'll have your periodic table, but you don't have to know how to read it. So in general, you got your metals, and then you got your stair step over here. These are your metalloids. And then you have your nonmetals here. All right, so you got to be able to identify an element on the periodic table and label it as metal, nonmetal, metalloids. Metals are conducting. Metalloids will conduct at low temperatures. Non-conducting are your nonmetals. So know your properties of metals. You can draw them into wire, pound them into sheets, things like that. Just be familiar with the various properties of your metals, your nonmetals, and your metalloids. There will be a multiple choice question on that. A homogeneous versus a heterogeneous solution. Well, so a mixture, because if you say the word solution, it is automatically homogeneous. All solutions are homogeneous. All right, so homogeneous versus heterogeneous. All right, so if you have any solution, if it says solution, that automatically puts it into homogeneous. So when we did our sand and salt, so a sand salt, all right, you could get a microscope and you could pick out the difference between the sand and the salt. That is a heterogeneous mixture. Then we added water, and then we had separated them. We added salt water, and we had the wet sand. All right, so that means it has water in it. And so salt water is a solution, and that is a homogeneous solution. Wet sand, that means sand that has water, definitely a heterogeneous solution. You can, as we did many times, we added more water to make sure all the salt was out. At the end there, we just had water and sand. easy to separate. You just pour out the water and then you dry it. And that's how we did our experiment in the lab. So know the difference between a homogeneous and heterogeneous mixture. Protons, neutrons, electrons, and nomenclature. All right, the easiest questions on the test are going to be protons, neutrons, and electrons. But if you don't know, it doesn't matter if it's the easiest question or not. All right, so if you had, let's say sodium 23, and you look at the periodic table, you're given a periodic table, and you see that it is element number 11. And so you need to know that the atomic number is equal to the number of protons. All right, so if it wants the protons and neutrons and electrons, well, your protons are 11, and you also need to know that your mass number is protons and neutrons. So you take your 23 minus 11, and you get 12. So the protons and neutrons must add up to your mass number. And I gave sodium without a charge. If it is an atom, all atoms are neutral. And if you are neutral, that means that your protons equal the electrons. All right, so if you have 11 plus charges, that means you have to have 11 minus charges. All right, so these questions would be the easiest. If we had Na plus, all right, so we just change it to the ion for sodium, which is sodium plus 1, and we'll say it's still the same isotope, which is mass number 23. Protons never change. If you're sodium, you have 11 protons. If you have 11 protons, you are sodium. All right, so your neutrons, this is always your mass number. All right, and so that's still 12. I didn't change the mass number. Now your electrons. For an ion, electrons do not equal protons. All right, if you have overall plus, you have more protons. If you're overall minus, you have more electrons. This one is overall plus. We have more protons. We have one more proton because it's plus 1, and so you have 10 electrons. So these should be very easy questions on the final. Make sure you get the easy ones right. Nomenclature. All right, so nomenclature, those are the hard questions on the test. You would think that that would be easy, but there's a lot of different things that you have to be able to name. All right, and it is going to be multiple choice, so you just have to be familiar with it. You don't have to know it well enough to come up with it yourself. You just have to know it well enough to pick it out of a lineup. All right, and so you know SO4 minus 2, you have to know that's sulfate. You also have to know that H2SO4 is sulfuric acid. And if you know that, you can come up with your own rules, and you don't have to memorize every, how do I name this acid? So you see what you did to the sulfate, you added the ic acid to it. All right, so sulfate is extremely common, you should know that. Sulfuric acid, extremely common, you should know that. And so then, of course, Cl minus, that is your chloride ion. And if you have HCl, now here is where things get a little more tricky. So if I put AQ, now it's hydrochloric acid. And everyone should know hydrochloric acid. All right, that's very common acid. We used it in lab. I don't know, many experiments use hydrochloric acid. All right, and so make sure you know that HCl is hydrochloric acid. And when it asks for something that you don't know, like HI, and you're like, I have no idea what that is. If you know what HCl is, well, then you definitely know what HI is. All right, because you have the periodic table, and you know I minus is iodide. And so it is hydroiodic acid. All right, so if you can do hydrochloric acid, you can do any of the acids that are in that same column. They are done exactly the same way. All right, but it could be HCl gas. All right, so you have HCl gas, and that is simply hydrogen chloride gas. All right, so with your HCl, if it's aqueous, all acids are aqueous. Okay, and then of course you have to know how to name your two nonmetals. All right, so everyone knows the name of CO2. If you forget your rules, go to names that you know. You know this is carbon dioxide. All right, and so you have two nonmetals. And so when you have two nonmetals, you have a molecular compound and you have to use the Greek prefixes. If you have CaCl2, now you have a metal with a nonmetal. So this one is molecular, two nonmetals. All right, this one is ionic because you have a calcium metal and then a nonmetal. All right, and so this is calcium chloride. On the multiple choice, you're going to have a choice of calcium dichloride. That is the wrong answer. All right, so make sure you know, and then if you come over here to this side, you know also, you should know CO is carbon monoxide. So if you're not sure if it's monocarbon monoxide, you know that you know carbon monoxide. So if it gave you SO, you would know that that is sulfur monoxide, all right? Because it's two nonmetals. You're going to name them the same as the ones that you know. All right, and so if you had NaCl, everybody knows that this is sodium chloride. All right, it is definitely not sodium monochloride because, again, you got your two nonmetals, and these are molecular compounds. You use the Greek prefixes. You have your metal and your nonmetal. These are ionic. You do not use the Greek prefixes. All right, so you will want to look at your polyatomic ions, you know, your NO3 minus nitrate, your PO4 minus 3 phosphate, NH4 plus ammonium, CO3 minus 2 carbonate, OH minus hydroxide, and MnO3 minus manganate, and ClO3 minus chlorate, and the rest of the list that was given. So make sure you're familiar with those. And then remember, go back to sulfate, SO4 minus 2. You can also have SO3 minus 2. All right, so this is sulfate. When you lose an oxygen, you get sulfite, ITE. All right, and so when you make that the acid H2SO3, remember this is not sulfuric acid, now it is sulfurous acid. So the ite goes to the us acid, the ate goes to the ic acid. And when you're naming binary compounds, they always end in IDE. All right, so any binary compound. All right, when you say a compound, it is neutral. If you say an ion, then that has a charge. And atoms and compounds are neutral. And if you have a binary compound, that means it contains only two elements. The name will always end in IDE. All right, so review your nomenclature. Again, remember, you have to know it well enough to pick it out of a lineup. It's going to be multiple choice. Strong acids and strong bases. All right, so this is going to be important for a lot of things. So you have to know your 6 strong acids. And what does it mean by strong acid? It means 100% ionized. All right, and so you have to know your HCl, your HBr, your HI, HNO3, HClO4, and H2SO4. All right, so those are the 6 strong acids. Again, you're going to be picking them out of a lineup. It's multiple choice. So you don't have to come up with them from memory, but you should be able to pick out the one that's either not a strong acid or the one that is a strong acid. That's the usual choices when you're doing a multiple choice. Or it could say which ones of these are strong acids as well. Your 6 strong bases. All right, again, just means 100% ionized. All right, so hydroxides are insoluble except for the 6 strong bases. Those are the ones that are 100% ionized. So you got lithium hydroxide, sodium hydroxide, potassium hydroxide. You've got your calcium hydroxide. I need my periodic table. Strontium hydroxide, barium hydroxide. Again, I have it memorized off the periodic table. It's the 3 that go this way and then the 3 that go this way. All right, so if I'm memorizing the periodic table correct, I got lithium, sodium, potassium, and then I got calcium, strontium, and barium. All right, those are the 6 strong acids. The ones in the first column are +1. They have 1 OH on them. The ones in the second column are in the +2 column. They have 2 OHs on them. And note, hydroxides, none of them are binary, and all of them end in IDE. Lithium hydroxide, sodium hydroxide, any hydroxide is not going to be binary, but is going to end in IDE. All right, so all compounds that end in IDE are not binary, but all binary compounds end in IDE. That just means there are some compounds that are not binary that end in IDE, and there are 6 examples right there. All right, so be familiar with your strong acids and strong bases. All right, and you'll need that for your molecular ionic and net ionic reactions. And so, let's see, which one do we want to do? Let's do AgNO3. This is one that we did in the lab. Well, you didn't do it. I did it. You watched it. AgNO3 plus HCl. All right, so you do a double replacement reaction. So your silver is positive. It goes with the Cl. So you got your AgCl. Is an ugly Cl, but that is a Cl. And then you have your H that goes with your NO3. All right, so that is a double replacement reaction. So these questions are going to be very difficult because you have to know if it's going to break up or if it's not going to break up. All right, and so when you see nitrate, all nitrates are soluble. And so that breaks up into Ag plus and NO3 minus. HCl, that's one of your strong acids. If it's a strong acid, it breaks up. If it's a weak acid, it stays together. Strong acid, 100% ionized into H plus, Cl minus. All right, and so one of the rules that you need to know for your solubility is all your halides are soluble except for silver, mercury, and lead. All right, and so this is a silver halide. It is not soluble. If you are not soluble, you are a solid. All right, HNO3, one of the 6 strong acids, H plus and NO3 minus. And so if it asks for the ionic equation, there's your ionic. So molecular, everything's neutral. Your ionic, if it is soluble, you put it in ions. If it's insoluble, you leave it in the molecular form. And then you have your net ionic. All right, and so we see that we have an NO3 minus and an NO3 minus. We subtract one from both sides. We have an H plus, we have an H plus. We subtract one from both sides. And so you end up with Ag plus and Cl minus goes to AgCl solid. And when you make a solid, it's a formation of a precipitate. And then, of course, your NO3 minus and your H plus, these are spectator ions. All right, so it could be any of these questions for your multiple choice. It could say, what's the molecular? What's the ionic? What's the net ionic? What's the spectator ions? What kind of reaction is this? All right, so that could be up to 5 different multiple choice questions on the one reaction. All right, so be familiar with your molecular, ionic, and net ionic. Again, you're picking things out of a lineup. You're not coming up with it from scratch. All right. Well, we can skip the balancing oxidation reduction. We didn't do that, but we do have to know oxidation numbers. We don't have to balance the reactions, but we do need to come up with the oxidation numbers. Right? And so you have to still know your oxidation numbers, and you have to still know what is the reducing agent, oxidizing agent. All right, so we're not going to do the difficult ones. We're going to do the simple ones like, let's say iron plus 2 plus Cr plus 6 yields Fe plus 3 and Cr plus 3. All right, so you have to see that your iron is going from a plus 2 to a plus 3. And so we write it in the half reaction. Iron plus 2 goes to iron plus 3. And we see that in order for that to happen, that is going to oxidize your iron. It went from a plus 2 oxidation to a plus 3. So this is your oxidation half reaction. All right, and to balance that, it requires 1 electron. When you have your Cr plus 6 going to Cr plus 3, you see it's reducing from a plus 6 oxidation to a plus 3. So this is your reduction half reaction. And on this one, you see that we need 3 electrons. All right. So when we add this up, we first have to multiply. We have to have the same number of electrons on the left and right. And so we multiply this by 3. And then we have the 3 electrons, cancel the 3 electrons, and we have our balanced chemical reaction, which is an oxidation reduction, 3 Fe plus 2s plus Cr plus 6 yields 3 Fe plus 3s and a Cr plus 3. And when you're done, you should check to make sure the charge on both sides is the same. So 3 Fe plus 2s, that's plus 6, and another plus 6. You got plus 12 on this side. On this side, you got 3 plus 3s, that's plus 9. You got a plus 3, and that is also a plus 12. All right, and so your charge on both sides would be the same. Remember that your reactant from your oxidation half reaction, this is your reducing agent, because if we were looking for something to reduce the chromium plus 6 to chromium plus 3, we would pick iron plus 2. That's why it's called a reducing agent. That is what's used to reduce your chromium. All right, and so the reactant of your reduction half reaction is called the oxidizing agent. All right, if you needed iron plus 2 to be oxidized to iron plus 3, you would need something to oxidize that called an oxidizing agent, and Cr plus 6 would work for that. All right, so you need to know your oxidation numbers. Let's do a few more that aren't as easy as that. let's go back to sulfate, SO4 minus 2. It could ask not what's the name of it, but what is the oxidation of your sulfur? Okay, that could be a very easily could be a question, because you then have to know that all oxygen's in the minus 2 column, and so each one of these is minus 2. So that's minus 8. We also know that whatever number we pick here, we get here for the S, when we add it to the minus 8, we have to get minus 2. And so simple math tells you that that oxidation of sulfur is a plus 6. And then if we went to SO3 minus 2, so now you got your minus 6, and now you got your plus 4. All right, so you have to be able to come up with the oxidations of things. Let's do H3PO4. So phosphoric acid. So another thing, everything in the first column. If you're in the first column, always plus 1 in compounds. Second column, always plus 2. Now you get to the transition elements, and you got multiple oxidations. So hydrogen's always plus 1, so that's plus 3. Oxygen's minus 2, so that's minus 8. All right, so you got to pick the thing here that, in this case, has no charge. All right, and so you quickly see that 3 plus 5 is 8. And so your oxidation of P in phosphoric acid is plus 5. So make sure you can get oxidation numbers. Chapter 4. I need my periodic table for this one too. All right, so we'll go with how many atoms of Br are in 5 grams of bromine. All right, so that would be an extremely hard question. Even if you know how to do it, you could still get the wrong answer because, again, that's an extremely hard question. All right, which leads me to the make sure you know your 7 diatomic elements, because most people that miss this will just have this as Br, and that is why you would miss it. You can have all the math right, but you don't have bromine as a diatomic element, and you're off by a factor of 2. So, know your 7 diatomic elements. All right, it makes a 7 on the periodic table. So you've got your nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All right, there's your number 7, except that's only 6 of them. Don't forget about hydrogen. Okay, so those are your 7 diatomic elements. So when you write a question like this and it just says bromine, or if it just says hydrogen or oxygen, all right, so that is going to be diatomic. But an atom is just 1. All right, 1 atom. Atom is just 1. How many atoms? 1. How many atoms? Bromine, 1, are in 5 grams of bromine. So you got to take your 5 grams, and there will be lots of conversion things to do on the final. Then you got to go to bromine and find the molar mass, which is 79.90. And that's why you would get the wrong answer, because it's not 79.90, it is Br2 here. And so it is double that. So you have to multiply it by 2, and you get 159.8. All right, and now you have moles of bromine. And remember Avogadro's number. It will be given, but you have to know when to use it. All right, so this is going to be either atoms or molecules per mole. All right, depends on what you're looking at. Br2, that is a molecule. If you have more than one atom, you are a molecule. All right, and so we have 6.022 times 10 to the 23rd Br2 molecules per mole. All right, so our moles of Br2 cancel, our grams of Br2 cancel. All right, so if the question was how many molecules of bromine are in 5 grams of bromine, which could easily be the question, there's your answer. But that was not the question. It was how many atoms of bromine. So you have to see that a molecule of bromine has 2 atoms. So there's 2 atoms of Br per 1 molecule Br2. So again, the reason why most people would get this wrong, but doing everything right, is they're off by this factor of 2 because they forgot that bromine was diatomic. Or they forgot that an atom is 1 Br, not 2 Brs. So you just multiply that and you get your answer. And again, it's going to be a very large answer. So it's multiple choice. If you're just going to guess, don't pick some very small number. You have a million, billion, trillion, whatever it's hecta things. It's 10 to the 20 something amount of atoms. It's going to be a very, very, very big number. So you can eliminate all of the small answers. It's going to be a large number of atoms. Atoms are tiny. You could never see an atom. It's going to take a lot of them to see it. And you can definitely see 5 grams. All right, empirical molecular formula. All right, so question will be, give the empirical formula of an organic compound that contains 40% carbon and 6.7% hydrogen. All right, so it will also say that this compound contains carbon, hydrogen, and oxygen. All right, so you have a compound that has carbon, hydrogen, oxygen. You send it off for elemental analysis, and you can get them to do everything, but it's very expensive to do anything except for carbon, hydrogen. Carbon, hydrogen percentages are very inexpensive. And so you just get the percent carbon and the percent hydrogen. And so you made your compound, and you know that it only contains carbon, hydrogen, and oxygen. And so it's got 40% carbon, 6.7% hydrogen. The rest is oxygen. So that means that your percent carbon, percent hydrogen, percent oxygen have to equal 100%. And so that gives you a 53.3% oxygen. All right, and so when you have this problem, you always then assume a 100-gram sample. Anytime I'm given a percent, I always do a 100-gram sample. That is not some magic number. You can pick any number you want. 100-gram sample is the easiest because that makes your percents into grams. All right, so if you have a 100-gram sample, that means 40 grams of carbon, 6.7 grams of hydrogen, and 53.3 grams of oxygen. All right, so you now have to get moles. So you divide by the molar mass. All right, and so you convert it into moles. All right, so you've got your 40 divided by 12. We only need 2 sig figs. All right, and then you have your 6.7 divided by, well, that's easy, that's 6.7. And finally, 53.3. Get your 53.3 divided by 16. 3.33 again. All right, so divide by your smallest number. And this one came out very nice. 1 mole carbon, 2 moles hydrogen, 1 mole oxygen. So that's your empirical formula. That is your C, H2, and O. All right. Molar mass was determined by freezing point depression. To be 180 grams per mole. All right, so freezing point depression, just like on the last test, you had your freezing point, then you calculate your molality, and once you have your molality and the amount of unknown you used, you can easily find the molar mass. So a very common way to find molar mass is freezing point depression. All right, and so now I want the molecular formula. And you're going to take the molar mass divided by the empirical mass, and that's going to equal an integer. All right, so when you take your molar mass of 180, and this is 12 plus 2 plus 16, 30. All right, so that is your empirical mass, and you see that you have a 6. All right, so it's C6H12O6. So this was glucose. All right, and glucose is a carbohydrate. And the reason why it's called a carbohydrate is because it has some number of carbons with some number of waters. The empirical formula for glucose is CH2O. So there'll be a calculation to do on empirical molecular formula. Stoichiometry limiting reagents. All right, so these are very difficult. Let's see, what do we want to pick? Let's pick something simple. Carbon plus oxygen yields. Oh, it's too simple. Carbon monoxide, that's fine. All right, and so put a 2 here, put a 2 here. You have a balanced chemical reaction. So first thing you have to do is balance. All right, normally they're balanced. You should always check to make sure that the equation that you're given is balanced. So if we had 10 grams of carbon and 10 grams of oxygen, and we produced 5 grams of carbon monoxide. So the question would be calculate limiting reagent, theoretical yield, percent yield. So limiting reagent, theoretical yield, and percent yield. All right, so you got to take your 10 grams of carbon and convert it to moles. Then you have to use the molar ratio, and you see that and on bottom you have to have your 2 moles of carbon will produce 2 moles of CO. Then we can convert that into grams by multiplying by the molar mass, which is 12 plus 16, which is 28.01 grams per mole CO. We do the same thing for the oxygen. We have 10 grams O2. And here's where people mess up. This is O2, 10 grams of O2. And so you have to have your 32.00 grams of O2 per mole of O2. So it's a good thing to put the actual compound in the grams per mole, especially when you're working with oxygen. All right, this is moles. This is how many grams of O2 we have. And so we then need the grams of O2 to cancel the grams of O2. Then the mole ratio, we see that 1 mole of O2 produced 2 moles of CO from our balanced chemical reaction. And then we convert that into grams, 28.01 grams per mole. Okay, so we get our numbers. All right, so this one, the 2 sig figs gives us 23. It's 0.3 repeating, but 2 sig figs in the 10 grams, we just need the 2 sig figs. All right, and then here, 32. 17.5. All right, so let's just make it 10.0, 10.0, and 5.00. All right, and so here we have our 2 masses, grams of CO, grams of CO. The smaller amount is your theoretical yield. And then what it comes from, the O2, so the O2 is the limiting reagent. All right, and so the last question was the percent yield. So you take your actual divided by theoretical times 100. The actual has to be given. In the problem, it was 5 grams was collected. 17.5 grams was the theoretical yield. 5 divided by 17.5. We have a 28.6% yield. So again, so we come back percent, so you multiply by 100, or you don't do that. And that's where you get your 28.6%. All right, so there'll be a problem very, very similar to this, where you got to convert what's given into moles, find out the least, which one forms the least amount of the product. That least amount is your theoretical yield. That reactant that it came from, that is your limiting reagent. and then your actual divided by your theoretical times 100 gives you your percent yield. So those questions are one of the more difficult ones you're going to have on the test. Diluting solutions and titrations. All right, so if we need 200 mils of 0.100 molar HCl, and in the lab, we only have 6 molar HCl. All right, so this is a dilution problem. So how do you make your 200 mils of 0.1 molar? All right, so this is a dilution. We are going to add water to the HCl. We have to calculate how we're going to do that. All right, and so when you have a dilution, molarity 1, volume 1 is equal to molarity 2, volume 2. Molarity 1, we have 0.1 molar, and volume 1, 200 mils. Now, molarity always has the same units, moles. Okay, so molarity is always moles, solute, liter, solution. All right, so volume has all kinds of different ones, milliliters, liters, centimeters cubed, meters cubed, whatever. For this, they just have to be the same units. All right, and so molarity 2, we have 6 molar. And then the question is, what volume of 6 molar do we need? All right, so to calculate that, we have to divide both sides by 6 molar. And you get 3.33 repeating. So to 3 sig figs, you get 3.33 repeating, 20 divided by 6. Yeah. All right, and so that is milliliters. All right, so that's your volume 2. All right, that doesn't tell you how to make it. So what it says is we need 3.33 milliliters of 6 molar HCl, but it doesn't say what to do with it. All right, for something this dilute, if they say assume volumes are additive. All right, sometimes you mix 2 solutions and the volumes, if you mix 10 mils with 10 mils, like alcohol with water, you get 18 mils. So you don't always have volumes that are additive. But in this case, when you're taking 6 molar and making it into 0.1 molar, you will have volumes that are additive. But never assume that the volumes are additive. If they will say if it is to be assumed. All right, and so we need 200 mils total, so we need 196.67 mils of water. All right, so what you do is you add 3.33 mils of 6 molar to 196.66 mils of water. Or the better answer, if they don't say that, you add 3.33 mils of 6 molar HCl to 190 mils of water, and then dilute to 200 mils with water. All right, so this is the way that you should always do it, but I know that sometimes that the problem will say assume the volumes are additive. All right, so you should never assume that unless the problem says. So whenever you're making a molar solution, you add what you need to add. All right, you had to have the 3.33 mils, and we have to have a total volume of 200, so we have to add it to some amount of water. Always add acid to the water. All right, so I am extremely confident that if I add 3.33 mils of 6 molar HCl to 190 mils of water, it's not going to go over 200. All right, you of course wouldn't say add it to 200 mils of water because now you're at 203.33. You could never dilute to 200. You have too much already. You have to make sure that when you add those two things together, it's less than the total volume required. Then you dilute to the mark with water. All right, titration. So MV over C is equal to MV over C. So let's say it's an acid and a base. All right, so it's just two reactants. It doesn't have to be an acid and a base. It could be the oxidizing agent, reducing agent. Whatever, it's the two reactants in a chemical reaction. Let's take also, if it's, so this is for liquids. For solids, if you are a solid, all right, so note here that M is moles per liter. It's an ugly L. And V is got to be in liters, so that the liters cancel the liters and you get moles. And so molarity times volume equals moles, N. All right, so that is one way that you can get moles. But here you have to make sure that your volume's in liters. If you want to get moles, this must be in liters. All right. If it's not in liters, well, then your liters don't cancel because molarity is always moles per liter. So volume would have to be in liters. But remember, many times when we're getting mass, like when we did our freezing point depression, we get our molality. To get moles in molality, you take your mass and divide by your molar mass. All right, and so you could have the same titration. So if you have an aqueous, if you have a molar solution, all right, you have that equation. If you have solids, now you got your mass over your molar mass, and C is equal to your mass over your molar mass, and C. All right, so we're doing acid base, oxidizing agent, reducing agent, but here the example is going to be acid base. All right, so if your acid is in the solid form, then you would use this. And then your base would be in the liquid form, then you would use this. And so you would then have mass over molar mass C for your acid is equal to molarity volume over C for your base. All right, so all it's giving you is the moles of acid divided by its coefficient, moles of base divided by its coefficient. It's just how are you going to get those moles? It's either going to be a molarity times the volume, or it's going to be a mass divided by a molar mass. All right, so in lab, we did, what we're going to do, we didn't do this, 0.1 gram of KHP, which is a monatomic acid. All right, which means monatomic means 1H. So this, and then it's going to be titrated with 0.1 molar NaOH. And it required 20.22 mils to reach the endpoint. Of unknown KHP. Oh, let's make that a 4. So 0.4 grams of unknown KHP, which is a monatomic acid, was titrated with 0.1 molar NaOH, and it required 20.22 mils to reach the endpoint. Now, KHP molar mass is given 204.23 grams per mole. That is an organic acid. It is not potassium hydrogen phosphorus. It is potassium phthalate, which is a organic compound. So it gives you the molar mass. All right, so unknown KHP means it contains KHP and it contains something else. And so what we're going to calculate, the mass of pure KHP. And so you have your mass over your molar mass, C, is equal to molarity times volume over C. And so the balanced chemical reaction is your KHP plus your NaOH goes to NaKP plus H2O. All right, so everything is 1 to 1. And so your coefficients are all 1. And so your mass divided by your 204.23 is equal to your 0.1 molar. And here's where most of the errors occur. This has to be in liters. All right, 0.4. All right, so as I said in the problem, I took 0.600 grams of unknown KHP. All right, so to find your percent KHP, you take part over whole times 100. So your pure KHP is 0.413. And then I changed it to 0.6 because, of course, the whole has to be greater than the part. And so go to our .413 divided by 0.6. %68.8%. So titrations would be very difficult. All right, so that gets us through the first 6 chapters. We can finish the rest tomorrow. No, not 6. That was only 4. All right, first 4 chapters. Last 2 you shouldn't need much song. And the final is Friday at 8 o'clock in here. Yes.